In the next problem, we consider a high-pass FIR filter which is designed using the given specification. So what is given is the frequency response should be HD of omega equals 0 for omega which lies between minus pi by 4 and plus pi by 4, and it is e power of minus j to omega between pi by 4 and pi. So we observe that in the initial part 0 to pi by 4 the frequency response is 0, and from pi by 4 to pi it is e power of minus j to omega. This is exactly opposite of a low pass filter, hence we can identify it's a high pass filter. Now here the problem is to be solved. Find the frequency response of the FIR filter designed using a rectangular window defined below. So that rectangular window WR of n is 1 between 0 to 4 and 0 otherwise. So it's a similar looking problem, but it's for high pass. Now let us sketch what we know. The sketch of HD of omega will look like this. So between 0 to pi by 4 to 0, and between pi by 4 to pi we have the value which is 1. Okay. Now the method of solving we shall see now. The inverse DTFT of HD of omega is computed now. As we know from the definition of inverse DTFT, HD of n is 1 by 2 pi of minus pi to pi. They are the limits. It's an integral of HD of omega, this is the input, multiplied with e power of j omega n d omega. This is from the definition of inverse DTFT. Now we are aware that HD of omega, how it is defined from the given. So we know that the value is found only between the region minus pi to minus pi by 4 and pi by 4 to pi. Therefore the limits you can observe, we start from the smallest limit minus pi till minus pi by 4. The expression for that is e power of minus j to omega, that is HD of omega, into, as per the formula, e power of j omega n. Similarly, the limit taken from pi by 4 to pi also has the value e power of minus j to omega into j omega n, e power of j omega n d omega. So therefore, now next part would be simplifying this. Now if you remember the last time when we did for a low pass filter, we got a term that is so we got a term which was sine of a quantity divided by pi times something like that, right? So here also we can solve in a similar fashion. If you want, we can perform the integration of this and arrive at the answer. So therefore, since the integrals both are similar, I'm not saying they're the same, they are similar, okay, performing the integration will give you similar results. The main difference lies in the limits, okay. So when you solve it, if you solve the integration, you will get the answer as sine pi times n minus 2 minus sine pi by 4 times n minus 2. Okay, the integration has to be solved. Okay, and common factor we have is 1 by pi times n minus 2. This equation is applicable when the value of n is not equals to alpha. Okay, and when n is equal to alpha, the integral now becomes 1 by 2 pi integration between minus pi to pi by 4, e power of this term becomes 0, e power of 0 d omega. The second term 1 by 2 pi integration limits are pi by 4 to pi e power of 0 d omega. Again we can solve this, and solving this integration applying the limits gives us the final answer 3 by 4. This is the answer we get for n equals to 2. The above is for n not equal to 2, this is for n is equal to 2. So we have got the HD of n. Now we have to find the impulse response of the FIR filter. So for the ideal case we found, so to get the finite impulse response, we take the infinite impulse response of the ideal filter and multiply it with the finite window WR of n, which is defined as below. WR of n is equal to 1, n between 0 to 4 and 0 otherwise. Then after doing the multiplication, you can tabulate the coefficients of HD of n and H of n along with WR of n. So by substituting the different values of n, in the problem we know n value, there are 5 points between 0 to 4, substituting, you calculate what is ht of n. Okay, once again, please observe it is symmetric about the midpoint. So computation of 3 points here may be sufficient. Okay, WR of n is 1, 1, 1. It's a rectangular window. Multiplication of the two gives the same answer. This is called as h of n. So we have computed the value of h of n. Next part, if the problem demands you to find the frequency response, then we can use the expression, because in this problem also n is odd, we take the same or similar equation that was taken in the previous problem. So this equation, once again, we can substitute the value of n is 5 and expand it, and you get the final answer after expansion, which looks something like this. So the result of the simplification is e power of minus j2 omega, where 2 is alpha. Okay, this is h of 2, it's a midpoint. The value you get is 0.75 as per the table. And then you have 2 times h of 0 cos 2 omega minus 2 times h of 1 cos of omega. So this is what you get after you do the substitution and expansion. Okay, so this is a method of solving the problem. In the problem here, we are given the statement as the desired frequency response of a low pass filter is given by ht of e power of j omega is equal to ht of omega is equal to e power of minus j3 omega, magnitude of omega less than 3 pi by 4, and for omega between 3 pi by 4 and pi it is equal to 0. Here clearly we can note that the value of alpha is equal to 3 and the value of omega c is equal to 3 pi by 4 for this low pass filter. Determine the frequency response of the FIR filter if Hamming window is used with capital N is equal to 7. Now, you may sketch the response. We know typical frequency response for low passer, how it looks like that, and we can indicate the cutoff frequency, pass band, stop band, etc. In the solution, from the definition of inverse DTFT, we have the inverse DTFT of HD of omega, which is given by HD of n is equal to 1 by 2 pi times minus pi to plus pi HD of omega e power of j omega n d omega. HD of n is the desired impulse response of the infinite IIR filter. Now, substituting the value of ht of omega, e power of minus j3n, the limits are modified accordingly. We have this value between 0 to 3 pi by 4 and 0 to minus 3 pi by 4. Therefore, in the range from minus 3 pi by 4 till 3 pi by 4, we have this value. Okay. Solving this integration will give you the result sine of omega c times n minus alpha divided by pi times n minus alpha. Therefore, the answer is this. This is for n value which is not equal to 3. Suppose the value of n is equal to 3, then the solution is given as hd of n being 3, is equal to 1 by 2 pi. The limits are the same, minus 3 pi by 4 till 3 pi by 4. The exponent power becomes 0 when alpha is same as n. So e raised to 0 is 1. Integrating it gives you an answer which is equal to 3 by 4. Okay. So the answer is omega c by pi. So since we have 3 pi by 4, which is omega c, dividing by pi, the answer is 3 by 4. This is for n equals to 3. So we have obtained all the points corresponding to hd of n. Next, we have to compute the impulse response of the low pass FIR filter. And to do that, the infinite impulse response hd of n is to be multiplied with the finite window function. So in this case, the problem mentions you use a Hamming window, okay, and the size of the window is 7. So Hamming window of size 7 means the n values to be solved is between 0 to 6. Now HD of n expression already we have obtained. We have to multiply it with the Hamming window function. The window function for Hamming can be written as 0.54 minus 0.46 cos 2 pi n divided by n minus 1 for n lies between 0 to n minus 1. If the problem was given for Hamming, then the formula would have been little different. It would have been 0.5 and 0.5 here. Okay. So this is the window function. Therefore, the impulse response of the FIR filter can be written as what we got for HD of n into the window function. So each term here we are multiplying with the window function. So this is the window function for Hamming. Similarly, here we have the window function for Hamming into 3 by 4. So 3 by 4 is the value of HD of n for n is equal to 3. When n not equal to 3, this is the expression. Now to compute the values, okay, so we can show the calculation as follows. So by substituting the values of n between 0 to 6 for 7 points, we can do the calculation of HD of n. We once again note it is symmetric. So if you calculate 4, the remaining 3 you can simply copy using symmetry. And the Hamming functions also have to be calculated. They also happen to be symmetric. And you know the product of those two is called as H of n. And this is also center symmetric. So this is the computation of impulse response. Now, since once again the problem is for odd, the frequency response of center symmetric FIR filter, the equation here is again the same equation, e power of minus j omega n times n minus 1 by 2. In bracket, h of n minus 1 by 2, that's a midpoint, and the limits are from 0 to n minus 3 by 2. If it was even, the midpoint term will not be there, and the limit would have become 0 to n by 2 minus 1. That's a small change which you can remember. And then expanding this particular equation will give you e power of minus j3 omega, where alpha is equal to 3, h of 3 because 3 is the midpoint, plus 2 times h0 of cos 3 omega, 2 times h of 1 cos 2 omega, 2 times h of 2 cos omega. You can see now as the value of h of 0, h of 1, h of 2 is incremental, whereas for the cos term we go backward 3, 2 and 1. So this will be the expansion, and next you can insert the values of h0, h1, h2 and h3 and we get the expression as shown here. So this is the expression for frequency response of the desired FIR filter. In the problem here, the specifications for an FIR filter is given in detail. They specify the passband edge frequency, stopband edge frequency, the minimum stopband attenuation and sampling frequency. Now the question states, obtain the coefficients of an FIR filter to meet the specification given below using the window method. They do not mention which type of window we have to use. The passband edge frequency is 1.5 kilohertz. Stopband edge frequency is 2 kHz. The minimum value of stopband attenuation is 50 dB. Sampling frequency is given as 8 kHz. This sampling frequency is very important so that we can convert the edge frequencies, which is in terms of hertz or kilohertz, into what is called as radians. Therefore, the first step is we wrote down what is given. The analog specifications are omega p is 2 pi f, the unit is radians per second. Omega s is 2 pi f radians per second. Ks is equal to minus as, which is equal to minus 50 dB. Next, convert it to digital specifications. We have to multiply, okay, to calculate omega, we have to multiply it with t or divide by fs. Therefore, here we know the value of fs, so we can divide it by fs and you get the answer in terms of radians. Therefore, omega p is 0.375 pi radians, omega s is 0.5 pi radians. Now in step 1, we observe that since the minimum value of stop band attenuation is 50 dB, we see that Hamming and Blackman window will satisfy this requirement. So looking at the table, we find that only these two will have a number which is more than 50 dB. So we go with Hamming window, the reason being that the Blackman has more transition width. Okay, Hamming is preferred, so we go with Hamming window. Now we have to determine the length of the window. How do you find N, capital N, or length of window? The transition width delta omega is calculated as omega s minus omega p. We find that the value is equal to 8 pi by n. Okay, as per the definition, we know that for Hamming window it is 8 pi by n. So we calculate the width, okay, and from this we can compute the order. The order can be determined here, or the size of the window is n greater than or equal to 64. Okay, at least we have to go for a value 64. Now we choose 65, which is an odd value, so that we satisfy the symmetry condition. So alpha should be equal to n minus 1 by 2. So to do this, n should be an odd number. So when you put n is odd, then n minus 1 is even, even by 2 will be an even value. So alpha is obtained. Okay, so alpha value is an integer. So we satisfy the condition by taking n is equal to 65. Now in step 3, magnitude and phase response of the desired filter is as shown in the figure. So we can start the design process now. So we are aware that the magnitude response for a low pass filter ideally will look like this. This is the shape of the phase response. Next part, as we have seen in the design, is to find the impulse response Hd of n. Now we know from the formula that it is 1 by 2 pi integral between minus pi to plus pi Hd of omega e power of j omega and d omega. Okay. Then we insert the value of Hd of omega as per our definition. You know it is e power of minus j omega alpha. And simplifying it, we end up with the expression sine omega c n minus alpha by pi times n minus alpha, n not equal to alpha. We are aware of the value of omega. Yeah, so when the value is n not equal to alpha, this is true, but for n is equal to alpha, we know the result is omega c by pi. Now, we are not sure about omega c, we have to calculate it actually. Omega c is given to be omega p plus delta omega by 2. So we choose it to be in the middle of the passband and stop band. It's a midpoint. So how do you calculate the midpoint? We take omega p and add it with the transition width by 2. Therefore, we get the answer 0.4375 pi radians. So we got omega c value. We know the order value. I think we can proceed now. So finally, the impulse response of the FIR filter h of n is equal to Hd of n times W ham of n. We know the window function for Hamming is given by 0.54 minus 0.46 cos 2 pi n by n minus 1 with n lying between 0 to 64. So this, as you can understand, the number of points being pretty large, we are not actually going to calculate the value of Hd of n, h of n and h of W ham, but it is possible. Okay, if you want a few values you can calculate, and you can say similarly we get values as follows. So this can be done if you're asked to design such type of problems.
Thank you all.